Hello, I'm Nicolas Usunier, and I'm going to present our work, Fast Online Ranking with Fairness of Exposure. This is joint work with Virginie and Elvis Dohmatob at Meta AI. We consider a ranking framework that represents online recommender systems. Users arrive one at a time, and the system needs to generate a ranked list of recommendations on the fly. While traditional recommender systems optimize for a proxy of average user satisfaction, which we call user utility here, we consider a more holistic framework where the recommender system should fairly allocate the exposure of items to users by taking into account the interests of both users and content producers. In this work, we consider exposure of items averaged across users, and the items recommended at higher ranks get higher exposure. Fairness of exposure received a lot of attention lately. We give here 3 examples that we treat in detail in the paper. First, it is sometimes desirable to boost the exposure of small producers to incentivize them to create content and maintain a healthy ecosystem of producers. Second, in order to avoid winner-take-all effects and popularity biases, it has been proposed that the exposure of items should be proportional to an estimate of an index of the overall quality of an item. The third criterion is introduced in this paper. We are motivated by some work on audits of job advertisement platforms. It could be seen as desirable to favor a balanced exposure of items to different groups of users defined by sensitive attributes. For instance, ensuring that the job ad receives a balanced exposure across different gender groups. Note that the implementation of this criterion incorporates many challenges, since, for instance, sensitive user attributes may not be available for privacy or legal reasons. We study it here from a theoretical perspective. Our main contribution is to show that in a wide variety of contexts, we can have fairness of exposure almost for free, in the sense of a small additional computation cost compared to not considering fairness of exposure at all. We consider a general framework where we see the recommendation problem as a fair allocation problem, and the resource to allocate is the exposure of items to users. In this framework, the recommendation objective can be written as maximizing a concave function of the average exposures of users to items. This is a difficult optimization problem because the exposure is averaged across users. This implies that the optimal rankings of all users depend on each other. Our main contribution is a new algorithm that solves this complex optimization problem online. It is very generic, as it applies to every concave function of exposures. Its main property are memory and computational efficiency. A simple sort at each step is sufficient. The overhead, compared to a system that does not consider fairness of exposure, is negligible. Importantly, we show that our algorithm enjoys strong theoretical guarantees, as its online performance converges to the theoretical optimum in 1/square root of number of time steps. In the remainder of this talk, I will dive in more details into the framework and algorithm, and I will briefly describe some of our experimental results. We consider that the recommender system must trade off between 2 terms, the average user utility and a criterion that depends on the exposure of items. Throughout the presentation, I will use the problem of balanced exposure as a running example. For balanced exposure, the goal is to make a trade-off between average user utility and promoting equal exposure of items across different user groups defined by a sensitive attribute. I first describe the recommendation objective and then the algorithm and the guarantees. The objective function f represents the theoretical objective of the recommender system. It takes as input a matrix pi of size number of users times number of items, which contains the average exposure of each item to each user. This matrix completely characterizes a recommender system, and the theoretical goal is to find values of exposure of items to users that maximize the objective function f. There are 2 sums in the formula. The first sum is over users, and the second sum is over items. Inside the square root, the variable s represents a protected user group. Vj given s is the average exposure of item j to users in group s. Vj given avg is the average exposure of item j. This objective function makes a trade-off between average user utility on the one hand, and on the other hand, the average over each item of the standard deviation of exposure across user groups. The standard deviation is used as an inequality measure here. Beta is a trade-off parameter, and higher beta means that we strive for more balanced exposure, potentially at the expense of user utility. Eta is here for technical reasons, only to ensure bounded second-order derivatives. Notice that this theoretical objective is static, and it does not directly depend on the ranking. It only depends on the exposures induced by the rankings. On the other hand, our algorithm strives to optimize this theoretical objective online and compute rankings at each time step. There are three main assumptions underlying our work. First, there is no learning. We assume that the user utilities, or equivalently the values of recommending each item to each user, are given by an oracle. The problem of jointly learning these utilities while optimizing a fair ranking objective is left as future work. Second, we assume that the user utilities follow a position-based model. This is a technical assumption that is usual in the fair ranking literature. The full details are given in the paper. Third, we assume that users arrive one at a time and that the incoming user is sampled randomly from a fixed distribution. In the objective function, the weights wi represents the probability of drawing user I at each time step. These weights account for different user activities. Users who come more frequently have a higher W. Our algorithm is called OFFR for online Frank-Wolfe for fair ranking, where Frank-Wolfe refers to a well-known optimization method we build on. We give here our algorithm for balanced exposure. At each step, the index I represents the current user. The algorithm computes one score for each item j hat ij. As detailed in the paper, the computation of this score is based on an estimate of the gradient of the objective function. The computation of these scores require O of 1 operation for each item, so O of m in total, where m is the number of items. The ranking is generated by sorting according to these scores. Here, k is the number of recommended items, and typically k is much smaller than m. The computation cost of our algorithm is thus similar to a standard pipeline which does not take into account fairness, since in all cases the process is to compute a score for each item and then sorting. In terms of storage, our algorithm only needs the v hat parameters needed to compute the j hat. These are counters that track the exposure of each item to each group. Such counters are necessary as soon as balanced exposure is of interest, so the additional memory requirements of our algorithm are minimal. In the full paper, we also provide algorithms for two other fairness of exposure criteria, two-sided fairness and quality-weighted exposure, as mentioned at the beginning of the presentation. Part of the main contribution of this paper are the theoretical guarantees for our algorithm. This table gives the details of the convergence guarantees we obtain for the three objective functions we consider: two-sided fairness, quality-weighted exposure, and balanced exposure. We call regret the difference between the theoretical maximum and the expected value of the objective function at time t. We prove that the regret decreases to 0 in 1 over square root of number of time steps in all three cases. In particular, this shows that our online algorithm converges to the theoretical optimum. We also give details of the convergence These formulas are discussed in more details in the paper. We now briefly discuss some experimental results. The main paper contains additional comparisons and baselines. We present experiments that show, in particular, that the algorithm converges faster at the beginning than an offline counterpart. On these plots, the x-axis represents time, and the y-axis represents the distance to the optimal value of the objective function. We compare our algorithm OFFR to an offline counterpart at equivalent computational budgets on the 3 fairness of exposure criteria discussed in the paper. Each plot contains convergence curves for 2 values of the trade-off parameter beta. Our algorithm, the bold large dashed lines, converges faster for each value of beta at the beginning, and the 2 algorithms eventually converge to the theoretical optimum as expected. The good performance of our algorithm at the early stages are promising results which highlight the potential of our ranking principle. In conclusion, we presented the first general algorithm for fairness of exposure that applies to generic concave function of the exposures, and we presented the details for 3 fairness of exposure criteria. Our algorithm has strong theoretical guarantees, and in particular, our work shows that fairness of exposure comes almost for free in terms of computation or storage costs. In this work, we did not address the problem of learning the user utilities. In the future, we intend to combine this ranking approach with exploration-exploitation principles. Furthermore, the criterion of balanced exposure is likely not applicable as is. In particular, but not only, because sensitive user attributes are not necessarily available in practice. We intend to study alternatives that do not require the knowledge of sensitive attributes.